Today we're going to talk about using the Laplace transform to actually solve differential equations. Of course, in order to do that, we need the one really important property of Laplace transforms, which is that the Laplace transform behaves very nicely when it comes to applying it to the derivative of a function. So let's see how that works. Suppose f is a nice continuous function and f prime is piecewise continuous on any interval from 0 to a. Suppose that further that there are constants k, a, and m such that the absolute value of f of t is bounded by k times e to the at for big enough t bigger than or equal to m. These are all just niceness conditions that say essentially things aren't too bad. F is continuous, f prime is piecewise continuous, and f doesn't grow too fast. Then the Laplace transform of f prime will have to exist for s greater than a, and moreover, you can compute the Laplace transform of the derivative f prime of t just by taking s times the Laplace transform of f and subtracting whatever f is at 0, that constant f of 0. Now, you might wonder, why in the world is this true? Well, it's actually a surprisingly straightforward thing to compute. The Laplace transform of f prime is just by definition the integral from 0 to infinity of e to the minus st, that's the kernel of the transformation, times f prime of t dt. And that can just be written as a limit, this improper integral as a limit as a approaches infinity of the integral from 0 to a of e to the minus st f prime of t dt. Now we just want to know, how can we compute this definite integral? Well, as long as f prime is continuous, we can just compute this integral in the standard way. We're going to use integration by parts. You might be used to writing a table here. When you're doing integration by parts, you have your u dv, your du, and your v. We're going to differentiate e to the minus st to get minus s e to the minus st dt. Our dv will be f prime of t dt, so that our v is exactly f of t. So that this integral is just the product on the diagonal, e to the minus st times f of t, evaluated from 0 to a, because it's the definite integral, plus the integral along the bottom, which has this s that we can pull out, times the integral from 0 to a of e to the minus st, that part, times f of t. Remember, we subtract, which cancels the minus sign there, so it becomes a plus, that integral. Well, when we put in this evaluation, we get e to the minus sa times f of a minus, I should have written, minus e to the 0, which is 1, times f of 0, and then this should have been here in the middle, plus s times this integral from 0 to a of e to the minus st f of t dt. Then we take a limit as a goes to infinity, which is what we want here. This part will go to 0 because our niceness conditions on f says that it doesn't grow faster than any exponential function. In other words, if f doesn't grow faster than a constant times e to the at least when s is bigger than a, this e to the minus sa will go to 0 faster than the f of a grows, and this whole first term goes to 0. And then what you're left with is exactly minus f of 0, plus the limit as a goes to infinity of this piece, which is exactly s times the Laplace transform of f of t, which is exactly what we have up here. Now, how can we use this amazing theorem about how to compute the Laplace transform of the derivative of f in terms of the Laplace transform of f? Well, I'll show you one simple example here involving solving an initial value problem. This is just a first order linear differential equation with an initial value. We have y prime minus y equals t, with our initial value y of 0 equals 3. And just for convenience of notation, we're going to let capital Y, and this is a function of s, be the Laplace transform of little y of t. So whenever you see capital Y, you know that's the Laplace transform of little y. We're going to talk about this later. We can get back little y will be what we call the inverse Laplace transform of capital Y. So little y of t will be what you get when you kind of run this Laplace transform backwards from y of s. Now, what do? We just take, if y prime minus y is always equal to the function t, then take the Laplace transform of both sides. Well, what's the Laplace transform of y prime? That's exactly s times the Laplace transform of y minus the value of y of 0. So this is s times the Laplace transform of y minus y of 0. That's all this piece here. And then we subtract the Laplace transform of y, which is this piece here, and that should be equal to the Laplace transform of t. Well, what is the Laplace transform of t? This is in the book, and we should have talked about this in one of our Zoom meetings. The Laplace transform of t, this is just the integral from 0 to infinity of e to the minus st times t. I'll just put that t in front, dt. And when you compute this, you'll see that this is exactly 1 over s squared. So this is the Laplace transform of t. We've now taken the Laplace transform of both sides. Now, you'll notice when we've done that, we've converted a differential equation in little y into an equation in big Y, but it's no longer a differential equation. We only have these capital Y's here. The point of the Laplace, using the Laplace transform, was that the Laplace transform of the derivative of a function just looked like, in this case, s times the Laplace transform of the function itself with the extra constant here that we had. You don't have a differential equation for capital Y, just a regular old algebraic equation for capital Y, which we can solve easily for y. We can write this as s minus 1 times capital Y is equal to, I'll put the 3 on the other side, 1 over s squared minus 3. In other words, capital Y is equal to 1 over s minus 1 times s squared. And then we have minus 3 over s minus 1. And we can put that all together by thinking this is 3s squared over the quantity s minus 1 times s squared. And we'll write this as, I'm sorry, that should have been a plus 3. Let's change that because that minus 3 going on the right side becomes plus 3. That'll become 3s squared plus 1 over s minus 1 times s squared. So capital Y is this beautiful rational function of s. Now, you might not think that looks so beautiful, but here's the amazing trick. We have ways to deal with rational functions of s to make them simple, and most of these are involved with the partial fractions method, which you all learned in Calc 2. And I'm sure that all of you really loved the partial fractions method when you studied calculus in Calc 2. How does that work? Well, let's take a quick detour into the partial fractions method. We have this function 3s squared plus 1 over a denominator which is s minus 1 times s squared. Now, the denominator is already factored because the first step in the partial fractions method is always to factor the denominator. And notice here the numerator has smaller degree than the denominator, because what I said before wasn't exactly true. If the numerator had a higher degree or even equal degree to the denominator, then the first step would be to do some sort of polynomial long division. But we're okay here. The numerator has smaller degree than the denominator, and the denominator is factored. So we can put this rational function into what we call partial fractions form, or maybe partial fractions final form, and write it as some constant a. We don't know what a is yet, but we know some constant will work over s minus 1. That's because of this linear factor s minus 1 in the denominator. And because here we have s squared, which is a repeated factor of s, we'll have two terms. We'll have a term b over s plus a term c over s squared. And now it's very easy to find the coefficient a here, this constant a. This will be true for some special A, B, and C. It's easy to find A just by the cover-up method. How does that work? We cover up this s minus 1. Imagine you've covered that up with your hand, and you plug in s equals 1 to the rest, and you get A equals 4 over 1, which is just 4. Why does that work? If you've forgotten why that works, do the following along with me. Multiply both sides by s minus 1, so this factor in the denominator disappears, but so does this s minus 1, and the other stuff gets multiplied by an s minus 1. Then when you plug in s equals 1, you'll get the 4 on the left. You'll get A isolated on the right because all the rest will go to 0 when you plug in s equals 1. That's really why this cover-up method works. Now, how do you get the coefficient of C? You can do the same thing with the s squared. You cover up the entire factor s squared, and you plug in s equals 0, and you get 1 over negative 1. C is negative 1. Unfortunately, this cover-up method only works when you have a linear factor of multiplicity 1, or when you have a linear factor with higher multiplicity. It only works on the term with the highest power of s here, in other words, the C term here. It won't work to find this B. So now we can write that 3s squared plus 1 over s minus 1 times s squared is equal to A, which is, we already know, is 4 over s minus 1, plus we still don't know B over s, and then we have minus 1 over s squared. How are we going to find B? Well, we can just use what I like to tell my students is a brute force method. It's just using algebra to combine all the terms on the right into a fraction over the same common denominator as we have here on the left. The first term is 4s squared over that common denominator, s minus 1 times s squared. You see that what I have there is just this first term. The b over s term is exactly b times another s times the s minus 1 over that common denominator. And then we have the third term, minus 1 over s squared, is just minus s minus 1 over this common denominator. And then we can expand out the numerator and write it in standard polynomial form. Here's the way I like to do it. Gather things up by powers of s in this case. We have 4s squared. Here we have bs times s is bs squared. So we have 4 plus b times s squared. How many things do we have multiplying s? We have bs times negative 1, and we have a minus 1s. So we have a minus b from here, b times s times negative 1, and we have a minus s, so I'll have another minus 1 times s. And finally, we look at the constants. The only place we have a constant is this minus 1, which is plus 1. Now this has to equal our original fraction on the left, so that since the denominators are already the same, the numerators have to be the same. Well, notice the plus 1 already matches the plus 1. We have the constant term correct. We need 4 plus b, the coefficient on s squared, to be 3, and 0, which is the coefficient on s, has to be minus b minus 1. We actually have 2 equations and only 1 unknown left, but it should be easy to see that solving these equations tells us that b has to be negative 1. Both equations are quite easily seen to be true when b equals negative 1. And now we know a, b, and c. In other words, this whole thing on the right here, 3s squared plus 1 over s minus 1 times s squared, is precisely 4 over s minus 1. Then we have b is negative 1 over s, and then we have c, which is negative 1 over s squared. Now, what do we have here? That's capital Y is equal to those things there. Well, what is little y? Little y is a function whose Laplace transform is capital Y. In other words, we want to take the inverse Laplace transform of capital Y to get little y. And the Laplace transform itself is linear. Similarly, the inverse Laplace transform is linear, so we can think of that as 4 times the inverse Laplace transform of 1 over s minus 1. Now, we've already seen that the Laplace transform of e to the t is just 1 over s minus 1, so when we work backwards, we have 4 e to the t. If that were the whole thing, the Laplace transform of y would be exactly 4 over s minus 1. But now we have this minus 1 over s. Well, what function has Laplace transform 1 over s? That's just the function 1. So we have a minus 1 here. And what function has Laplace transform, which is minus 1 over s squared? Well, we've already seen the Laplace transform of t is 1 over s squared. So the Laplace transform of minus t is minus 1 over s squared, or the inverse Laplace transform of minus 1 over s squared is just minus t. So here we have it. My claim is that this function here is our solution to this initial value problem. And we know this initial value problem has to have a unique solution, which is valid everywhere. We can check that. What is y prime? Y prime is easily seen to be 4 e to the t plus 0 minus 1. And so that y prime minus y, which is this minus this, is exactly t. That checks. What is y of 0? When you plug it in here, y of 0 is what we get, 4 e to the 0 minus 1 minus 0. That's 3. That checks. This is, in fact, the unique solution to this first-order linear differential equation, and we found it by using Laplace transforms and some fun with partial fractions.